Hello and welcome to the Chartered Institute of Ergonomics and Human Factors and our online event today regarding human factors in military aviation, past, present and future. So a fascinating topic on the table for you today, as all our topics are, but this one in particular, I think. So you'll be hearing in the next minute or two and over the next 75 minutes or so from Fiona, from Lucy, from Susie and from Jean, and pulling us all together will be Steve Harmer, our facilitator today, and I'll be handing over to Steve in just a second. Just some rules of the road for you. I know they'll be pretty familiar to many of you, but here we go. You can enter whatever you like into chat. Well, I say whatever you like advisedly. Comments, questions, etc. please into the chat box below. It helps if you can just preface your question with a Q for question, colon, and then off you go. That helps us to pick out questions from comments. That's just very useful. If you can keep your question fairly brief, I know some of them may be complex, but to the point, that also helps us to direct your question and to understand it. That would be great too. So that would really help us. All right. If you do have any audio or visual issues at all, then please firstly close down your browser and re-enter the room. That's by far the easiest way of getting yourself straight. Give that a go first, and thereafter, if that doesn't work, just check your audio settings to make sure they're correct. Okay, the other thing to note perhaps is that Chrome and Firefox are notoriously reliable browsers for this, Safari to some extent. So if you're trying to use anything else, particularly if you're trying to use Microsoft products like Edge or Internet Explorer, then probably best to use another browser. That's the top tip from me, I think. Okay, well, without further ado, I'm looking forward very much to the next hour and a quarter, and it's my pleasure now to hand over to your chair and facilitator today, Steve Harman.
Thanks, Steve. Good afternoon, everyone, and welcome to the CIHF Defence Sector Group event. My name's Steve Harmer. I'm a human factors engineer working for MOD Defence Equipment and Support. That's the part of the MOD, Ministry of Defence, responsible for procuring equipment and services for the UK Armed Forces. The Institute's Defence Sector Group was rebooted last year following a couple of meetings with the Institute's management team. The group is led by me and my colleague Laird Evans, and it forms a link between the Chartered Institute and the long-established UK mod industry HFI, Human Factors Integration Liaison Group, and its associated steering group. The Liaison Group has been active for more than 30 years, supporting the development of UK mod HFI policy, process and guidance. And many of you attending today will have contributed to the work of that group over the years. The Defence Sector Group has organised 2 webinars this year. In November, we'll be looking at the contribution of human factors to the design of military land vehicles. More details on that will follow. But today our focus is on human factors in military aviation. And I'm delighted to welcome our team of 4 speakers from BAE Systems at Warton, Lancashire, who I'm sure are well known to many of you. Our speakers are Fiona Kayser, Lucy Twigg, Susie Broadbent and Jean Page. Between them, they have many years of experience in the application of human factors methods, guidance and process to the design of military air systems. And I know that this is going to be a presentation which demonstrates the important role that human factors plays and continues to play in the design of these increasingly complex and high-tech systems. So thank you for joining us today. Please use the chat facility to raise any questions you may have. We'll get a chance to discuss those at the end of the presentation. I'll now hand over to Fiona, who will provide a more detailed introduction to the presentation team. Fiona.
Thanks, Steve. It's lovely to be here. I'm really pleased to bring with me today 3 of my female colleagues for International Women in Engineering. As Steve said, we've got quite a varied background between us, some 80 plus years of experience, which is we're going to share a little bit of that with you today. We've got loads to get through, so I will dive straight into the agenda if that's okay with everyone. So we'll begin the presentation today with a brief history of military aviation, so a little bit about cockpits and also about the human factors therein. The main part of the presentation will be a number of case studies. So today we're going to give you 3 manned aircraft case studies, and we'll explore 1 unmanned case study. And then we'll wrap up the presentation with a look into the future and what challenges we're expecting and where we think we have to go. So into our brief history of aviation. So on the screen there, you can see a number of cockpits over quite a vast period of time. So when we look at cockpits from way back in the kind of 1910s, we're really looking at some simple cockpits. There's very few instruments or controls in the cockpits themselves. And a lot of those actually came from the automobile or even boats world, you know, the very simple dials and knobs. As we move forward by sort of 20 or 30 years, we're starting to get a little bit more in terms of controls and displays in the cockpit. You can see there, it's a bit of a grainy picture, but we are giving the pilot a bit more information about the aircraft that they're flying, and sort of understanding a bit more about what they need. By the time we get into sort of the 1960s, really you can see that human factors has started to be introduced, and we're organising the cockpits a little bit better. We're starting to introduce some basic sensors into the cockpit, things like radar, better display technologies. And I think this is around about the first time that ejection seats were also included. So we were starting really to think about how to protect the pilots a bit better. 1980, so we're looking at sort of the Jaguar cockpit. You can see there again, it's more modern, there's more technology in there. It still is very full of dials and controls and so on, but we've started giving them multifunction displays in the cockpit. They have other technologies such as night vision goggles and so on. So really we're starting to give the pilot a lot more data and organise the cockpit better. And then into aircraft that are actually flying around today. Eurofighter Typhoon, you'll see that a lot as we go through this presentation. That really is sort of a glass cockpit concept. So multifunction displays, fewer actual physical controls in there. Head-up displays to allow the pilot to stay eyes out of the cockpit and still safely fly the jet. And so when we look towards the future, what do we anticipate the cockpit looking like? You hear a little bit later on in the presentation about some of our future work in the Tempest programme, but really we're sort of now looking at what technologies would be best placed to put into the cockpit. The amount of data that's available out there is vast, so we need to really support the pilot in analysing that data and figuring out what they want to do, when they want to do it in the best way possible. We're also feeding into things like the white paper that CIHF put out on future aviation as well. So we're constantly trying to develop. So that's the cockpit. Now if we look a little bit more about the people who actually fly those cockpits, we see a sort of a similar story to the cockpit evolution. When we think about what pilots were wearing to fly in the 1910s, you can see there it's not really much more than a waterproof overcoat, maybe was the best thing to describe it as. They've got a leather flying hat and some gloves. Not an awful lot of protection really against the elements, given that a lot of these cockpits weren't even enclosed at that particular point in time. As we move forward, say to the Spitfire, for example, we've started to provide the pilots with things like oxygen and some goggles so they can actually see when their head's out of the aircraft in the cockpit. We've started thinking about protecting them if things go wrong, so providing things like parachutes. And there was lots. This was really the start of the development of our aircrew equipment research and trying to make things better. So by the time we get to the 1960s, you can see there the pilot's clothing is significantly different. We've got G-suits, we've got proper helmet protection on there. The flying suits are lightweight. We're giving them oxygen. They have gloves and boots and life preservers. And then towards the 1980s, so kind of modern really, and what a lot of aircrew are flying now, We've got the kind of standard green grow bag, as we call them. They've got immersion suits, so if they happen to have to eject on land in water, helmet is much better in terms of the technology and the materials it's made out of. And we have just basically much better protection for the pilot in the conditions that he has to fly in. And then as we are looking into sort of the 2010s, again, it's not really changed a significant amount, to be honest. We still see the standard grow bag. Obviously, our immersion suits and stuff have improved slightly, but not significantly. So as we look forward into the future, we should really be looking at taking sort of the modern materials that are out there, really thinking about the weight of the equipment that we're putting on the pilot in the cockpit itself, and understanding how they're going to operate and in what sorts of environments. So that really was a whistle-stop tour of how things have evolved over time. We're going to move on now to the 4 case studies that I mentioned. So we have 3 manned case studies. So that's the Hawk aircraft, the Typhoon aircraft, and the Nimrod MRA-4 aircraft. And I think we've only got time for 1 unmanned case study. So they will be brief overviews. You can imagine we could probably talk for an hour each on each of those case studies. But please, if you've got any questions, put them in the chat and we'll try to get to them as we move towards the end of the presentation. So the first case study, I'm going to hand over to my colleague Lucy, who's going to come and tell us about some of the work that she's done on Hawk. Lucy, over to you.
Thank you so much, Fiona. So I'm going to, I can't move the slides on. Can you hear me okay, Fiona? I can't move the slides on. Could you move on to the next slide? Sorry. Apologies for that. So I'd like to pick up on that that theme of technology development that Fiona's been talking about, using the Hawk aircraft as an example. You might be familiar with the Hawk. The Red Arrows are an old variant of the Hawk aircraft. It's traditionally used, though, as a training aircraft. We have 2 cockpits, a front and a rear cockpit for the instructor and the student. When we release any new mark of aircraft as a company to a customer, we must give them a set of anthropometric clearances. So those are a range of body sizes that can and cannot safely use our aircraft. Could you just put me on the next slide? Sorry. Thank you. So a fastjet cockpit is quite a restrictive anthropometric environment. We have to make sure that our users can safely reach all the controls, all the safety related controls in the cockpit. And we must make sure that we've got physical clearances, especially because we've got an ejection seat. So we don't want to leave any parts of the operator behind when they eject, so we must make sure that we've got the physical clearances in there. We must make sure that they can see, they've got a direct line of sight, and in inverted flight and G, we must make sure that they've got the correct clearances. So we have to work to issue those values. So on the next slide, we'll talk about how we traditionally do anthropometric clearances. So I've lost the slides, I can't see anything. So traditionally, we were asked by our customer, can you fulfill a range of anthropometric sizes? So we'll be given, for example, a range of 5th to the 95th percentile for our anthropometric clearance. And what we'd do, we'd get participants, physical participants who are close to those limited values, and put them in the cockpit and carry out assessments. So if somebody had got 5th percentile functional reach, we would ask them to do reach assessments in the cockpit there and determine if they can reach or not. But that question has actually changed subtly over the years, from can you clear X to Y. The question now from our customers more is what can you clear? So although the wording is very subtle, it actually changes massively the way that we approach making our anthropometric clearance documentation. So on the next slide, hopefully, you should be able to see a picture of a coordinate measurement machine. So we use a Faro arm. There are different ones out there, so I'll probably refer to it as a Faro arm because it's a bit easier to say. So hopefully on the picture you should be able to see, on the right there, you should be able to see a picture of the Faro arm, and people that aren't familiar with them, you'll see it comes to a point on one end, and when you press the trigger on that, it will give you an XYZ coordinate in space of where that specific point on the arm is. So we can use that within a cockpit to give us an XYZ coordinate within the cockpit when we use it. So on the next slide, you should be able to see one mounted to the cockpit frame. The reason that we mount the coordinate measurement machine to the cockpit is aircraft move. When people are getting in and out of them, they do move slightly on the wheels. So if we brace that Faro arm to the aircraft, it all moves in phase, so we don't lose that calibration there with the cockpit. So you should be able to see a picture of one of our subjects in the rear cockpit of a Hawk aircraft, and what we ask our subjects to do, we know their physical measurements, they're pre-measured before they get in, and we ask them to carry out a number of tasks in the cockpit. So it might be to reach a specific switch, it might be to control the rudder pedals or move the stick. And when we're doing that, we measure with our Faro arm, measure specific areas on the body, specific physical landmarks on the body. So then we've got those XYZ coordinates of the participant, each participant in the cockpit while they're carrying out those tasks. And if we go on to the next slide, you will see that all of the thousands and thousands of data points that we gather across a full assessment, you can hopefully see a handful of those on the slides there. So just to try and explain the picture that you see in, because it's a bit of a framework, on the right-hand side, towards the bottom, you should see a grey, bluey block. You can see it's almost a cube shape with a stick down. So imagine that's the headrest of your ejection seat, and then you'll see a little to the left, you'll see a little yellow item, that's your control stick in your cockpit, and then you'll see almost a cutout framework as well area in there, so that would be your instrument panel in your cockpit. So you can kind of imagine the bare bones of a cockpit there. That's in our 3D design tool that we use. So those points that we've measured in space, immediately we can drop them into the cockpit there, so we know precisely in space where they are. So we take all those XYZ coordinates and we run them through a series of equations. So on the next slide, you'll see a graph. It should be it's a graphical representation of the equations that we carry out. So we use those to understand each participant is a certain body size, and we've asked them to do a certain task. Let's say we've asked them to reach a switch. Now we can understand how far past that switch somebody has been able to reach, how short of that switch they have been, and through studying all that data and producing our equations, we can therefore see what is the perfect functional reach to be able to reach that switch and not reach past it, not underreach it, but reach exactly on. So then we can give a minimum clearance for that functional reach for that particular parameter. So you can see how we get, the next slide just shows how we use digital data essentially. So how we would use a Faro arm in a cockpit to give us all the digital data points that would allow us to produce a number of equations to give a full anthropometric clearance for a cockpit. And that's how we've developed anthropometrics over the years to give our anthropometric cockpit clearances. So next I'll hand over to Susie, who's going to talk about Typhoon. Thank you very much.
Hello, is that working? Oh good, I should presume it is. Okay, so moving on to Typhoon, I must caveat this by saying I am a bit out of date on Typhoon. I did 5 years in Typhoon cockpit maybe about 5 years ago, so this is very much based on my time in the group then, but I don't think things have changed too much, but I will stand to be corrected by more recent members of cockpit group in the chat, who I'm sure will have something to say about this. So the role of Eurofighter cockpit group was the first time really in military aviation that the cockpit was delegated a system within its own right. Traditionally, you had all the different engineering areas being responsible for their own displays and then arguing about where they should go within the cockpit. Whereas with Eurofighter, it's very much taken from the standpoint that the cockpit system, we have to design for the human usability of that. As Fiona mentioned, there's a lot more displays, there's a lot more sensors coming in. So we need to be able to present all that information in the right way. So Cockpit Group was set up back in the late 80s, I believe, and it was made up of systems engineers and human factors specialists. And their roles, as you can see there, were to define, agree, specify and certify all of those pilot interfaces within the cockpit. So in terms of the geometry, like Lucy's been talking about in the anthropometrics, making sure everything was reachable by the people we were contracted to provide for. So Eurofighter, probably worth mentioning, 4 nations. So we have to fit the Italians, the Germans, the Spanish and the UK within the cockpit. And each of those had their own different anthropometric requirements as well. So the geometry, the layout, and then the displays and controls, which is really where a lot of the human factors initial work was done. Previous generations of jet, like the Tornado, for example, very much had computing power, but it was almost less than a megabyte. You could have green on black or black on green. That was essentially as complicated as your color choices got, let alone anything else within the software. So Typhoon, it was really important to get the displays and controls and style guides and things agreed for them. So the considerations for Cockpit Group are the human factors requirements, the human error, the environment, the physical ergonomics, and the cognitive limitations perhaps of the individual involved in it, because Typhoon is a single seat aircraft. So traditionally, again, on Tornado, you would have somebody in the front and somebody in the rear, and you would have 2 different versions of that aircraft, one for ground attack, one to air attack. And essentially what we did with Eurofighter was take all of those and put them together in one person. So there was real drive there to try and make sure that just the single seat could still do this, whilst also meeting the operational requirements of the jet and, you know, being in line with the system and equipment capabilities. So the jet itself, in terms of the human interface, we've got a cockpit, so 3 multifunction head down displays there, stick in front of you, throttle to the side, and that piece of glass in front of you is your head up display, which can overlay green information on the outside world, just so you can look out and you can see information overlaid on the real world. What we also have though is the helmet. So this is the Striker 1 or the helmet equipment assembly, or various other terms. Electric hat, the RAF referred to it as for a while. So this just allowed you to take that information that would traditionally be displayed in the head-up display and take it with you as you moved your head around. So you didn't have to keep referring back into the cockpit. You could spend more time looking out. So those are the things that we were responsible for within Cockpit Group. The design process that we followed, as I mentioned, human factors were involved from the very start. So we produced documents like the ergonomics handbook, which was essentially a user guide to save everyone having to read all the very fascinating defence standards. We'd cut out various bits of that to present it in a style guide for the engineers to use. We also developed the principles of cockpit moding. So that's it, what information should be presented where, what buttons should go on your HOTAS, your hands on throttle and stick, so it's quickly accessible. What do we do in terms of warnings? So we had all these style guides and standards and philosophies done from the first get-go, really. And then throughout the life cycle of Typhoon, as I mentioned, Cockpit Group is still going today. There's still constant upgrades going on. So every time it's going back to the requirements capture, understanding what the requirements are, doing the analysis of it, developing designs, doing the usability acceptance, formalizing the design, and then keeping going through, clearing it into service, etc. So lots to do, lots to get involved in. As I mentioned, within the team, the systems engineer and HF specialists. Also, we have close relationships with our industry test pilots and the customer aircrew, just to make sure that when we do deliver something, they're actually going to accept it. But also airworthiness and people like that as well. So lots of people involved, even though it's a team of systems engineers and human factors people, we obviously have to communicate to the wider avionics, the customer community, etc., etc. So when I joined Cockpit Group, the human factors focus was very much on doing assessments. So we were brought in pretty much to carry out the assessments in line with our human factors guidelines. We have a number of facilities available to do this. So we've got the active cockpit rig, we had a mission development lighting cockpit and an ambient lighting facility. So I'll just go on to speak a bit more about these. If it doesn't crash, I've got a spinny circle. Can you all still see the slides? I'm quite happy to continue talking if that keeps.
Susie, yes, we can see the slides.
Right, okay, which slide are you on at the moment? Mine's just crashed.
We're on 21, layout assessments.
Layout assessments, hooray. Okay. So the layout assessments are much like what Lucy was talking about before. So the anthropometrics, the way we did it in the day, we were very lucky within Typhoon Cockpit Group to have people who fit the 5th and 95th percentile, as you can see from that picture of many of Cockpit Group at the time dressed up in their AEA. So the cockpit had already been designed by the time we were working on it, and this was essentially just to look at any modifications or any alterations. We'd get a flight suited up and go in and just test so that we could verify anything we did additionally would still fit within the cockpit. Always a fun day when they made you put your aircrew equipment on for winter sea. It's not a pleasant ensemble. Okay, next slide, please. So the ACR moding assessments, these are assessments that were carried out at various stages during design development. So the active cockpit is a simulator and emulator. It allows us to run real missions. It allows us to use, put pilots in there, and we can design missions and we can get them to try out various things. So each time we do a new bit of software, a new big release, we'd call in the pilots from the different 4 nations to come and assess it, and we develop missions. And again, another joy of Cockpit Group, having to sit in the control room and to pretend to be air traffic control or a wingman while they did these various missions. So we'd bring in the 4 nations pilots, the guys I mentioned before, but also first to shake it down and make sure that everything was okay, our operational test pilots, the people based within the companies, so all the different partner companies that we work with, to shake it down and make sure that we were on the right lines. They'd come in and they'd have a thorough briefing and be trained by the Cockpit Group engineers who'd often done the design, and they would say whether they'd agreed with the design, and then we'd go on and test it in missions. So next slide, please. I think I'm on 23 now. How we'd assess this, we would do subjective questionnaires, quick and easy questions, multiple choice, some answered whilst they were still in the cockpit. So we'd brief them on how to do the Bedford rating scale, for example, and every so often at various times during the mission, we just ask for a workload score over the comms, because we don't want to interrupt too much. We want some level of fidelity still in there when we're doing it. But it's a lot easier to get workload scores, we found, during the mission as opposed to ask them to recall it at the end. And if they didn't answer, we just presumed they had really high workload. We also had observers sat in the control room, so you could see in the control room all the different displays that the pilot could see. You had an air traffic control map where you could see where you were having various hostiles and targets and things come in. And we'd have measures of effectiveness. So we'd have basically performance measures that we could tick off. Have they remembered to check in with air traffic control? Have they reached time on target? Things like that. So we'd be responsible, the human factors engineer, plus the engineer who designed that in the control room, and if we could get them, our aircrew as well to come and help support, although flying often took precedence to helping out with cockpit assessments, as you can understand, but they did turn up on some occasion. But also we had objective measures. The active cockpit being as it is we could get logs from it of which buttons they'd pressed, how much time they'd spent with each display up. And over time as well, we started to use the eye tracker to be able to say exactly what they were looking at, exactly what they were doing as we were carrying this out as well. So we'd do all that, and then at the end we'd come up with a list of recommendations, and then it would be back over to the nations again to invite them in for what's known as a wash-up meeting, where they would argue out what requirements would go forward into this. So that was Typhoon, and I shall now hand over to Fiona, who'll talk a bit more about the assessments that they did on Nimrod.
Thanks, Susie. Hopefully you can all see and hear me okay. So Nimrod, the MRA-4 Maritime Reconnaissance Aircraft, a bit different to the other aircraft that we've been talking about so far. It's a much larger aircraft. It carries multiple crew, and when I say multiple crew, the Mark II, which was the variant before this, had 4 people in the flight deck and 10 people in the back. So much bigger aircraft, some real human factors challenges compared to some of the fast jets, really. So the aircraft itself was a multi-role aircraft. It could do lots of different activities, but that included things like anti-surface warfare, but also search and rescue. So it used to go out and look for ships or even people in dinghies that needed rescuing. So from a human factors point of view, there's a huge number of different challenges. One of the main things is there's no ejection seat. So if they have to get out for whatever reason, they can't just pull a handle. We've got differences like onboard catering facilities. So, you know, they could stay up in the aircraft for a good few hours. And so we had dining facilities, they had cooking facilities, and they also had space for passengers. But unlike the other aircraft, which had HMI, so human machine interface, just in the flight deck, you can see in the bottom right hand picture there, we had 8 people down the back on the new variant that all had their own individual workstations. So we had integrated human machine interface between the front and the back of the aircraft. I'm just really going to touch on one of the challenges that we tackled on the MRA-4 program, and that was in the flight deck, where they wanted to reduce the crew from 4 people, so there's 2 pilots and 2 flight engineers. They wanted to reduce that down to 2 people in the cockpit, and they wanted us to prove that that workload situation was acceptable. So you can see that top right hand picture there, that's the Mark II flight deck. It is 30 years old. I think the first flight for the Mark II was about the 1967 timeframe. Very heavy in terms of dials and knobs, very old-fashioned looking. And bottom centre, really, that was the new design that we came up with. As you can see, it was very much based on the glass cockpit concept. And we did that really focusing on workload, what the pilots had to do in the cockpit and understanding what information they needed. We used a lot of different techniques. Some of you in the audience would have been involved in those, and our good host this evening, Steve Harmer, certainly was involved in some of the predictive workload analysis that we did. So understanding what the aircrew had to do in the flight deck and looking to see where we could use automation to make that easier or to remove those tasks and allow the system to do those tasks for the pilot instead. And ultimately, taking all of those bits of information, we designed the new flight deck that you can see at the bottom there, and we went through a lot of testing in order to prove that that was actually acceptable in terms of workload. So I just have one slide here which talks about what we did. Just like the Susie was talking about, we do a lot of human in the loop assessments. And really, we created a high fidelity simulation environment. So you can see that in that big picture in the center there, that was our flight deck assessment rig. It was a very realistic representation of the cockpit. One seat is missing just for photographic purposes from the cockpit, but it has 2 seats in there. It was very immersive, so we could run representative missions in there. And those missions didn't just last sort of 1 or 2 hours like they would for a fast jet. They were multiple hour missions. And basically, we threw everything that we could at them to make them as realistic as possible. Susie touched on training the pilots, so not only did we have to train the pilots in terms of operating the new flight deck, but also in terms of the different techniques and tools and techniques that we wanted them to use in order to assess all of their performance and the new design itself. Taking sort of Typhoon's learning, we really took on board sort of gathering complementary data sets. So not only did we ask the pilots what they thought, but this time we also gathered objective data. That was either directly from the simulator itself, in terms of things like, did they maintain the flight level that they'd been cleared to? But we also had expert observers looking at the performance, assessing what they were doing, whether they'd made any errors, whether they were aware of everything that was in the mission itself. We measured workload, and again, as Susie alluded to, we had to teach them how to use those workload measures so that they didn't become confounding factors. And one of the other things that we did was we introduced this concept of red lines for our different tools and techniques. So we tried to determine ahead of assessments what good was and what bad was. So where on the Bedford rating scale or the NASA TLX scale did we think acceptable workload was, and where was unacceptable workload? And we used those red lines really to agree with the customer that that's the criteria we were going to measure against, but also it allowed us in our data analysis process to identify what we called hotspots, so areas that we wanted to really focus in on when we were kind of debriefing them afterwards, after the mission was finished. One of the things really that I wanted to pick up on this is that from what Susie said, and also from the Nimrod example, we base a lot of our data gathering from high fidelity rigs, and they do take a lot of time and effort to create, and are obviously very expensive. So as we're going forward and looking into the future, we need to really be thinking about what else could we do, how else could we be assessing human in the loop type assessments. And you hear a little bit later on about some of the technology that has evolved really in terms of how we could measure pilot workload. Could we start including things like eye tracking and some of the other psychophysiological measures that are out there? And would that be a cheaper, better, quicker way of measuring pilot workload? Anyway, food for thought. I'm sure Jean will touch on it in the future section as we get there. Oh, I've lost the slides. Just hold on 1 second. Okay, I think I'm back. Can somebody confirm that you can actually see me still and hear me? Yeah, okay, brilliant. Thank you. Okay, so that was the end of our manned case studies. I'm going to move on now to a single unmanned case study. And again, this is a little bit old now, but it is cleared for public presentation, so all is good. And I think we, this, if you see the picture on the left-hand side there, that is one of our test assets. That's the Jetstream aircraft. And the other pictures are part of our ground control station. So if we just move on to the next one. Okay, good, it hasn't crashed. So operating an unmanned aircraft really gives us a lot of slightly different human factors challenges than we do have in manned aircraft. So firstly, the person, the pilot, is not in the vehicle itself. They can't see what the vehicle is doing, can't see out the window unless there are sensors on board to allow them to do that. But they can't hear what the aircraft is doing. They can't feel what the aircraft is doing, or the environment that it's flying in. So really, they're totally reliant on the information that's being sent back from the aircraft to the ground. And passing that information from the aircraft to the ground can take time, depending on the bandwidth that you've got. And so that can add delays to the information. And so one of the challenges from a human factors perspective is, how does the pilot know how old that data is? Are they making decisions on that data in real time, or has it been delayed in some way? Secondly, if the pilot is pushing commands up to the aircraft, that can also be delayed depending on how wide the bandwidth is, and that can have an impact on the other aircraft, other air users. So a second's delay in asking the aircraft to turn, for example, could have catastrophic consequences. So that one of the studies that we did, and the one I'm going to go through with you now, is really focusing on the human factors challenges and trying to understand what we need to consider with an aircraft that may be operating in the same environment as other manned aircraft. So the project that I'm going to tell you about was a project called ASTRAEA, and ASTRAEA stands for Autonomous Systems Technology-Related Airborne Evaluation and Assessment. And I had to put that on the slide because it takes all my brain power to remember what that stands for. But it was a research program, and we were really looking at the impact of operating an unmanned aircraft in airspace with other aircraft in there. And although it started off as a research program, we actually did fly that Jetstream aircraft that you saw on the previous slide from Wharton in Lancashire all the way up to Inverness in Scotland, unmanned. So we were able to fly through the airways, we were interacting with air traffic control and other air users. So it was a really powerful demonstration piece. But this particular study that I'm going to show you about, again, involved a synthetic environment where we were simulating the unmanned aircraft itself. We were able to simulate air traffic control in real time. We had, you can see top right-hand corner of the picture there, that was our ground control station. So that was where the operator or the pilot sat in order to control the aircraft and to understand what it was doing and where it was going at any point in time. And bottom right-hand corner there, you can see that is some of the air traffic control sectors. And so, as I say, we had people role-playing air traffic controllers during those assessments. And we captured the same sort of things that we would capture in a standard human factors assessment. We were really interested in things like situation awareness, workload, what mistakes did people make, and how was the performance impacted by not actually being on the aircraft. But you can see there, one of the different things we had in was to do with trust. And really, the reason we had trust in there was because what we found was that people, where things were being done automatically, I'm going to avoid the word autonomous here, where things were being done by the system, the operators didn't naturally trust it. They very much needed to see that the system was being transparent, so they had to understand what it was doing and why it was doing it, and it didn't take much for that trust to be eroded. And then as a consequence, what we found was that the operators took control back from the system, and that increased their workload. So quite interesting in terms of human factors challenges. But what we found through quite a lot of those assessments was that this concept of how the human interacts with the unmanned aircraft within airspace, it was viable. When you get into the world of unmanned aviation, there is a lot of talk of the operations being transparent and equivalent to manned aircraft. So what that means is that air traffic control don't really want to know that the aircraft is unmanned, they just want it to behave like a manned aircraft. So as the operator is not sat in the aircraft, that can give us some challenges. But we found that despite having delays necessarily in the communication between the air traffic control and the ground and back up to the aircraft, they were able to comply with all of the instructions that air traffic wanted to give them. And they were able to detect and avoid other people in the airspace itself, and they could understand what the aircraft was doing and how it was going to do it. If we look forward to kind of the future considerations, again, technology comes to the fore, really. There are some huge developments that have gone on which will really help the operator to interact with the vehicle and to understand what's going on. And you can see some of them listed on the screen there. But I think one of the major things from a human factors point of view, certainly from my own personal perspective, is that we need to understand what the role of the operator is going to be, or the role of the pilot. really, in an unmanned aircraft, the pilot or the operator is not going to be flying the aircraft in a traditional sense. They really are going to move more to sort of a mission manager or a controller in a wider sense. And so how best can we support those operators, and who would they be? And again, it comes back to, you know, we've used simulations for a lot of this work. And could we actually move maybe towards more model-based assessments? There's a lot of talk, certainly, in our engineering industry about model-based systems engineering. So it's all good and exciting stuff, but it's understanding how it will work best for us in the human factors world. So I'm now going to hand over to Jean Page, and she will share with you some of our thoughts on the future and where we should be looking. Jean, over to you.
I'm hoping that you can hear me. If somebody could confirm that, that would be good.
All good.
Excellent. So the bit I'm going to talk about is kind of going on from where Fiona's talked about, and I'm sure some of you have seen some of the things that have been in the press that Susie's communicated with respect to what we're doing for our next generation aircraft, which is Tempest, and some of the work she's doing on psychophysiological. So I'm going to touch on some of that, but really I'm going to try and give a bit of a wider flavour as well. So I think the first thing I wanted to say, my slides have gone black now, so that's excellent. Again, if somebody could move the slides on to the first slide and make sure that we're all okay, that would be good. But we're living in a time where we're witnessing quite a step change in technology, and particularly in the pace of technology development. And we're seeing that, you know, across the patch really. A lot of the technologies that we're now looking at in defence, if you looked at the pictures Fiona showed at the start, they're very much traditional technologies that you would see in most cockpits. But I think a lot of the technologies now are coming from the commercial and civil markets. But as the MOD Joint Concept Note that was published in 2018 says, the kind of challenge really, we've got robots, artificial intelligence, autonomy, but it's important to recognize that in our future systems, at the core of future military advantage will be the effective integration of humans and machines. And I'm sure Steve, as the chair of the MOD HFI group along with LED, would kind of absolutely back that up. And from our perspective, there's a kind of view, and Paul Shah kind of argues in one of his documents, the report on robotics in the battlefield, the winner of the robotics revolution will not be those that develop the technology first, or even who has the best technology, but those people who figure out how best to use it. And I think a key part of that really is the human side of it. So as I said, we are seeing more in the way of artificial intelligence, autonomous systems, robotics, and the other thing I'd bring attention to is something we call ubiquitous sensing, which is capable of generating and distributing petabytes of data around the system. And this kind of approach is really going to change the world we live in, both in anticipated ways and unanticipated ways. And I think what it creates for us as human factors engineers is really a degree of uncertainty about what that future world looks like. And when we talk about products that are in service for 50 to 70 years, how do we manage that uncertainty? You know, a lot of this is we know the technologies are going to need to be upgradable. They're going to need to be adaptable and flexible. But above all, they need to be capable. And I think what we will see is it's kind of what Fiona alluded to, which is it's the role of the human that we're likely to see change quite a bit. If we can go on to the next slide, please. I'm hoping this is an environmental slide. So from an environment viewpoint, what is it that we need to consider? The first thing I think I'd like to note, I've put some example strategies on the right-hand side there, is we really are seeing a fairly consistent strategic view, whether you look in Australia, Europe, the UK. It's a fairly consistent view of what we expect the world to change. Of course, whether it's right or not is quite another matter. We may just be all feeding from the from the same data, if you like. But we're also seeing a degree of consistency from a human factors viewpoint. There's a shameless plug there for the white paper that was produced by the CIHF last year on the future of aviation, and then a more recent document that came out in May this year, the one on human augmentation from the MOD. I've mentioned the increased use of autonomous and robotic systems. Through a lot of these systems and through the data that I was talking about, we're really very much heading towards machine speed warfare. We talk a lot about the OODA loop, the observe, orient, decide, action. And with the kind of generation of aircraft that we've had in the past, that's very much been something that the human can control. I think where we're going now is where we can expect to be going is that this stuff will become so fast that it's hard for a human to process the amount of information that they need and make the decisions in the right kind of timescales to get advantage. We're also seeing from the military more of a risk appetite and a desire to look at solutions that are not from the traditional defence sector. So only a couple of days ago, the chief exec of DSTL put out an open letter urging industry, academia, engineering, science and technology to work with UK specialists to combat future threats. And we're certainly seeing, when we think about some of the technology we're looking at, that we're seeing the developments in those technologies really occurring in the kind of gaming and entertainment markets, and also in the health sector, where perhaps the first use of the technologies is as medical therapy, and then as time goes on, they become more about how we augment human performance. The other thing that's worth noting is the threat environment is expanding and becoming increasingly diverse. It includes the cyber and space environments now, as well as land, sea and air. And I think the approach we are going to need going forward is to become less siloed in our traditional domains and to consider it more as a single coordinated, what we call mosaicked battle space. And by mosaicked, what I mean is the kind of idea that it's a multitude of parts, but that are operating in an integrated and interoperable system, where potentially you don't have controllers of individual assets, but you have somebody who has situation awareness and is commanding, controlling and communicated with that whole battle space environment. That it's almost that the platforms themselves could almost be agnostic and transparent to the user who's really delivering a mission to a goal. The other thing we need to note, I think, is that the adversary is going to be increasingly capable. All this technology that we will have access to, they will also have access to, and they'll use them in ways that we do not anticipate. So we really need to move fast to resolve issues. And then the final point on this slide I wanted to mention was that we also talk about warfare in the grey, and certainly we'll have seen a lot of this in the last 5 to 10 years. This is stuff where it's actually sort of sub-threshold of war, that the thresholds have not been crossed, but it includes a lot of disinformation, intimidation, cyber hacks. Whether you look at the US presidential elections or whatever, there's evidence that increasingly this is happening. And how do we respond to that? So moving on to the slide on human augmentation, I hope we are on the right slide. We've communicated quite a lot so far on cockpits, but actually much of the technology and the approach that we take is equally applicable to other applications within defence. And I think we talk about the pointy thing, the platform, if you like, but increasingly when you look at how long our products are operable for, a lot of the products that we provide are more on the service side, whether they be the training, maintenance support, data analysis. Increasingly, the information advantage space is going to be quite large. So a lot of these technologies and the approaches that we take in human factors are just as applicable in these applications. If I look in our manufacturing environment, we are looking at collaborative robotics that allow a human operator to be closely integrated in with the automation systems, as opposed to perhaps what we've had on robotic lines so far with the humans excluded. These kind of things are driven by issues such as affordability, quality, the accuracy required, say, of applying glues or whatever it is that the manufacturer is doing. The key to it is obviously safety. an acceptable risk to users and bystanders, and the training and awareness and acceptance of some of these technologies for our future manufacturers. In terms of the factory of the future, a lot of the technologies that are going in there will just be equally applicable in the maintenance environment as well, although they might need to be looked at in a slightly different way. But you can imagine what the hangar of the future might look like. From a mission support viewpoint, we have areas like mission planning, mission rehearsal, tactics development, the whole data analysis perspective. The moment the aircraft, the amount of data coming off an aircraft, after a mission, a lot of it goes without being analysed within a reasonable timescale. And if you can't analyse the data in a reasonable timescale, then you're not getting the information out of that data that might help you with performing your missions. From a training perspective, I'm expecting a major change in this area, whether it be impacting the trainees or the instructors, whether it be reducing the time to achieve competency, getting better outcomes, individualizing the learning. To date, it's rather been a one-size-fits-all. Susie talks about the use of psychophysiological monitoring for that purpose. We're going to see increased use of synthetic devices, but also with a reduced infrastructure. Some of the assets Fiona showed you in some of the pictures, you can see they're quite large, and maybe you only have one of them. With technology such as AR and VR, there is a real possibility of providing reasonable training devices at point of need, whether that be the home environment, the squadron environment, or wherever, much more cheaply, and to allow the use of those technologies at an individual pace. But critical to all of this, and again, from Laird's perspective, I'm sure he'll be pleased to hear me say that really one of the things we have to take is a human factors integration approach, because whether you're talking about the instructor, the trainee, the support engineer, the data analyst, with the use of these technologies, the increased use of autonomy, it is absolutely critical that the roles that we have in defence are roles that humans want to undertake. Certainly, if I go back to the prime of automation, if you like, the idea that the human is just there to monitor the system is not a role that I think most of us would find attractive. And I certainly think for some of the decisions that we need these people to make in defence systems, it's not a role we should be perpetuating. Going on to look at some of the technologies themselves, it's a bit hard to predict how technologies will mature. I started my career back in the 1990s, and the first thing I investigated was future cockpits. And we had some virtual reality devices, and it has taken till now for those devices actually to become mature enough that they really can start to make a difference. As I said, many of these are developing in the commercial and consumer sectors. We've got technologies on the left here in the timescale that we're showing, such as exoskeletons. We're seeing those in factories already, where they're wearable devices and they can support the human with physical performance, reducing the physical burden and reducing the hazard. On the far right-hand side, you might see something like teleexistence, where I can imagine a maintainer could be wearing virtual reality devices along potentially with an exoskeleton and some haptic devices that allow them to feel the environment, which could make them actually control a robot arm in a maintenance environment that was 1,000 miles away or whatever, in a high-risk environment, but they would feel that they were doing it, and perhaps they would do that for things that a robot was not yet capable of doing or had not yet learned to perform. We have techniques like brain stimulation technologies, and again, some of those have their roots very much in medical therapy technologies. So transcranial direct current stimulation is one example of a current day depression treatment, where the US, in particular, the US Air Force, have evidence that it does improve cognitive function if you're exposed to this current stimulation for a certain time, and it also decreases the effects of fatigue. So the one thing I can say for sure about this chart is the horizons here are incorrect. But what is key for us in the defense industry is to understand the impact of these technologies and how they will impact the way that humans interact with systems and what role they should undertake. The other thing about these technologies I'd note is that it's almost impossible to take the kind of approach we did for things like Nimrod and Typhoon, where we were heavily dependent on the prescriptive nature of standards. And with the way technologies are going, that we can't have those kind of prescriptive standards. We need much more of an approach that makes sure we do the right thing, but perhaps not necessarily expressing the size of a button or the size of text or the color of text that we should use. It should be much more based on proving that the system is safe and effective. If we go on to the next slide, I think I've got some examples. Now we've got I'm hoping we're on a slide that shows the kind of Tempest view of life of how we're developing cockpits. So we are looking at what Susie called a wearable, software reconfigurable cockpit. And that is really because that gives us the flexibility that we think we will need going forward, recognizing that our products are in service for a long time. The environment is changing, the threat is changing, and therefore we need something that we can rapidly upgrade in an affordable manner and that can take advantage of new technologies as they come along. If you go to the next one, I think that's on psychophysiological measures. Again, I'm not going to dwell too much on this because Susie recently gave a talk on this, but we are looking at how we can monitor the state of the pilot, both physically and cognitively. Physical might be from a safety viewpoint of, are they conscious or have they passed out due to the effects of G or hypoxia? From a cognitive viewpoint, there's the viewpoints like fatigue and workload. How do we make sure that the human and machine are working at an optimum level? We can use the same measures in training, and we can also use the same measures in our design of our assessments. And then I think the final slide that shows some of the technology is something like an environment where it might be more like battle space management, where you're just in a room where you can reconfigure the table to look like any interface that you want. If I go on, I hope to a slide that kind of shows a little bit about the design process. I think Fiona mentioned model-based systems engineering, and I think one of the things we need to be cognizant of with this technology change is it's actually going to change the way we do our work as well. Increasingly, the intent is through model-based design, at least in the defense sector, that we will have what we call a digital design, a through-life digital thread, if you like, where the design will exist in a digital way and perhaps not in a physical way. And we need to be able to design, develop, and test our products increasingly in a digital way. And the challenge for us, I think, as human factors practitioners is, well, how do we represent the human in that? You saw lots of pictures of some of the assessments we've done in the past where we'll have aircrew or even aircrew representatives come in and we put the right clothing and things on them, but we'll test the system with perhaps 8 people or 8 aircrew coming from different nations. And one of our problems has always been with those 8 people is they are possibly the most experienced people. Well, how do you make sure that your design is suitable for somebody that's just qualified? So the challenge for us as to what we will need to give to engineers is how do we represent humans in model-based systems engineering? You can see that, my slides come back. You can see from what Lucy talked about that you might be able to do that from the viewpoint of including physical mannequins that represent the size and the body mechanics. But even with those, we've generally found that what they can't fully do at the minute is represent the movement of the body when wearing all the equipment that the person will be wearing, and with contents in the pockets, you get a slight difference in the way that the system is used. Nevertheless, our engineers are going to be using this kind of common visualization and digital product environment and need support from us to better understand how we represent the human. So what are we going to do from a human behavior viewpoint, attention, reaction time, and representing human errors? I also think more than ever, we've always been, as a set of practitioners, an area that needs to engage with a lot of others. I think that's just expanding. So whereas previously we've worked with systems engineers, I think increasingly we're going to see the need for multidisciplinary teams where there's expertise on robotics, biomedicine, electronics, artificial intelligence, and a whole bunch of other things. And I think it's where you get that cross-discipline team that will be where innovation occurs. And I think it's a real challenge for us. We need to embrace the tool sets that others are using and make sure that the human factors view, whether that be goal-based task analysis, workload assessment, or all tools that we can embed as part of those as well. Probably rambled on a bit, but I think that was my last slide. So I hope that was at least coherent, given that I couldn't see any of the slides.
Thanks, Jean. Hopefully you can see me now. I've picked up some questions as we've been going through amongst the chat about people falling off and losing slides, so apologies for that. But I picked up a few questions, and I'll run through them as I can. The first two are, I think, probably best directed at Lucy. They were to do with the sort of anthropometrics, and we were talking about Hawk at the time. So it's a question from Sean McDonald about how we account for AEA and the clothing sizes, clothing allowances when we're doing some of the anthropometric studies. And similar to that, how do we account for the allowance for future growth of the target audience? Lucy, I don't know if you've got an answer for that.
Yeah, absolutely. That's a very interesting one. So when we carry out our in-cockpit assessments with our participants, we do indeed make sure that they're wearing the correct AEA. And as Jean stated later on, we make sure that they're carrying the correct kit in their pockets and everything's padded out. We also need to make allowances for things like G-suits inflating and make sure we've got clearances for when those inflate during flight. In terms of future growth of cockpit participants, I guess my answer to that is that we fully explore the complete capacity of the cockpit now. So instead of that old question of can you fit this narrow clearance, this specific clearance into the cockpit, we really are exploring the bounds of everything that the cockpit can accommodate. So we're getting that full clearance out of the physical geometry of that cockpit now.
Can I add to that, Lucy? I know on the Nimrod aircraft we had a weight growth allowance. I saw in the comments some comment on middle-age spread, so that probably was about that. And we also on F-35, the clearance on F-35 was for people from a 4'10" female to a 6'7" male. So it was in a very large anthropometric range in the first instance.
Thank you. There was a question also for the section on Typhoon, Susie. It's from Siddharth Siam Sundar. Was there a reason we have the information displayed on the HUD and the helmet-mounted display when it could be just on the helmet-mounted display?
Yeah, it actually does. As you move back into the vision of the HUD, there are various overlaps so that you don't have to see it twice. It was just in case there were issues with the helmet, you'd still have that information there because it was very new technology at the time. But as I say, that they are engineered together so that you don't get that double overlaying at the time.
I think the F-35 is the first one that has had the clearance to do it without a head-up display. And again, that represents the technology has moved on, and there's confidence now that you can certify the primary flight reference and that the HMD is reliable enough without the need for a HUD.
Okay, thank you. We moved on to talk about Nimrod, Fiona, and Harriet Morley had the question, which obviously occurred to her from DSDL. When we were doing the studies looking at human performance, workload, situational awareness, you talked about redlining, did we have to go through ModRec approval? So MOD's Research Ethics Committee approval?
We didn't for the measures that we took. So the measures where we had red lines were mainly the workload and situation awareness measures. So things like NASA TLX, Bedford and so on. We did agree those up front with the customer at the time. So our human factors customer representatives, and also we used aircrew observers. So we discussed it with them before we set them, and really they were a means to an end. So they weren't necessarily black and white, but it helped us to kind of have that rapid debrief after every mission, so we could almost identify hotspots immediately by having some kind of threshold to measure performance against.
Just jumping on that, the recent work we're doing now, we've started including things like the eye tracker and some of the psychophys stuff. That ticks one of the boxes, which means we do have to go to MODREX for that, because it's very much personal biological data, whereas before, because it's just subjective data pretty much, that we didn't have to go through that, whereas now, yes, we are familiar with the process.
Thank you. There was a question right at the beginning, actually, which probably relates more to some of the presentation slides at the end. So probably a question for Jean or maybe for Susie. So Justin asked, what's been the role of functional neuroimaging, neuroergonomics, in designing and evaluating interfaces, and what's the role expected to be in the future?
Susie, do you want to take this one?
Is Jean telling me to answer that one? I couldn't hear her, but I could see that look on her face that she's directing it towards me. So yeah, that's very much the intention. At the moment, we are just trialing these technologies in the lab to make sure that they are giving us the data that we'd hope they'd give us. So there's lots of academic papers out there saying that yes, these will give you an indication of workload. The first ones we started doing were the ones with the eye tracker on the Typhoon cockpit group that I mentioned, which were very much done just to be able to say yes, they need that information in the helmet. Because the helmet, the first instantiation of the helmet, was limited by how much drawing they could do on it, how much information we could present. So we started to use an eye tracker to say, no, the pilot is definitely looking out at this time, therefore it needs to be in the helmet. But again, it brings us into that MODREX issue. As soon as we start taking these measures, we're going to have to go through the MODREX procedures. So we want to make sure that they are giving us the valid evidence that we need before we do that. So I'd expect over the work we start doing on Tempest, when we start doing more intense assessments on the Tempest HMI, that we would be using them as part of that, definitely.
I think there's been a kind of evolution in how we do testing and measurement. So if I go back to the beginning of my career, that we probably had a very strong reliance on subjective data, asking the operators what they thought, and they were the experts in the use of the system, and therefore that was a very valid thing to do. And we still continue to do that because they're the users, that they understand how the product's going to be used. Increasingly, as we went into areas like Nimrod, we used objective data, and Fiona talked about the workload stuff, and a lot of that was, can they do the task? Did they land, or if it was F-35, did they land on the carrier at the right spot? So there's objective data, subjective data with rating scales, things that you can measure. I think where Susie's taking things now is okay, we've got the subjective data still, we've got the objective data still, but at what cost to the human? So it's kind of like trying to get a bit of that window into the soul, if you like, of yes, the human is doing the task. Yes, the human is achieving the task, but at what cost? Whether that be fatigue, workload, are they really looking at the things and seeing the things that we would expect them to? So all the measures that Susie's trying to take is really to try and give us that additional insight over and above what the user may consciously be telling us.
Or deliberately obscuring from us. That there is a certain type of, operator that may not want to admit that they have in workload issues. I've had pilots nearly, give a workload score of 2 out of 10 and then almost fly into a mountain because they don't necessarily aware of what they're not aware of, particularly when we start asking questions about SA, about situation awareness. It's very much, well, do they know what they're missing kind of thing? And that's where stuff like the eye tracker can really help as well. Generally, I've taken the approach there that if someone gives me 9, 10 out of 10 for workload, even if they haven't had the workload that high, they're obviously trying to flag something to my attention that they think needs to be fixed, and they are willing to admit that it's a high workload because of that. But yeah, it's trying to get away from just that individual, this pilot says so kind of things that we can be at the mercy of.
Thank you. Fiona, we talked about Australia, and I've got a question really there. I've never been involved. So you mentioned at the beginning that one of the challenges for an unmanned system is that the controller, the pilot, can't see, hear or feel the information. And I wonder whether there were any studies done either as part of the Australia programme or maybe prior to try and provide that kind of information to the remote controller so they experience the airborne environment whilst remote from the air vehicle.
Yeah, it's a really interesting question, that, Stephen. It is technically possible. The thing that limits is the bandwidth, so the size of the pipe that the data are travelling from the aircraft down to the control station. If you're limited in some kind of capacity, then the data can be old. I kind of referred to that in the words that I was using before. But equally, you might want to actually be sending data down to the ground that is helping you do your mission rather than just allowing you to see out of the window. One of the things we did explore on Australia was field of view of the camera. So forward-looking cameras, what can it see? And that was really focused around, can we show that technology is equivalent to the pilot's eye? So, for example, if we're asking the pilot to keep watch out for other airspace users, if we were trying to replace that with technology, is technology good enough? And very quickly we realised that the field of view of some of the sensors that were available was actually quite narrow, and so it didn't give you that equivalent sort of look and see. Interestingly, on some of our other unmanned assets I didn't talk about today, we have pumped the engine noise down to the ground. It doesn't take much bandwidth to send that back down to the ground, but it gave the operators, the pilots at the time, a bit of a comfortable feeling that the engine was still running rather than relying on sort of the indicator, the silent indicator on the display in front of them. So we have done things like that, and it is that human kind of component that's a real challenge. I coined a phrase, certainly in some of the other unmanned stuff I've done, about challenging the comfort blanket. So as I think Jean or Susie said, we do tend to use sort of SMEs that are at the top of their game. They are the real experts in either how the system works or what the environment is around about it. But equally, that can mean that they are quite I don't want to say old in their views, but they're kind of stayed in their kind of assumptions about how a system should be designed and should be operated. Whereas with the advances in technology, we can really push those comfort blankets now and start to use some of the new things that are out there and that are developing, at a rapid rate of knots. So we're really in the future systems designing for people who are either in primary school or maybe not even born yet. So it's a real challenge.
Can I add to what Fiona said then? I'm going to point at Pete Gibson, who's online. That'll teach him to be popping up all the time. I know we did a bit of work a while ago called Loss of Cues, and I think Pete was the author of it. And that looked at things like, what cues do you lose when you're trying to control remotely? And, having the speed that you're doing in a remote aircraft and the height doesn't tell you whether the engine is still working, if you know what I mean. Whereas that sound, as Fiona kind of said, that's a cue. If that goes quiet, you've lost the engine. It's a fairly fundamental cue. So for me, this goes very much back to, one of the things I think we're quite clumsy with, and this is just generally now with remote control of vehicles, is that we've kind of put that pilot in the monitoring role. And that's exactly what I'm talking about. That's an inappropriate role, in my opinion, where we're then trying to feed them signals that are very bad signals, and they're trying to monitor things that tell them that the engine is still working. And the one fundamental, which was, can I hear it, has gone. So for me, that's kind of where some of the challenge comes of what's the role of the human? And if we've got them monitoring that the thing is flying based on a 3-figure digit that's moving very slowly, that's a poor use of a human. And I think we have to really look at what is the human role in these future systems and fight the systems engineers who want to put them into the role of monitor.
Great, thank you. Conscious of time, there was one last question from Sean McDonald, which asked about how does HF apply to a radar operator in the ops room in the Combat Information Centre on a warship? Seems an odd question to ask when we're talking about military aviation, but I think it's a good cue for another webinar in the future, looking at human factors in maritime systems. So I know Harriet Morley's on the phone, on the call, and I know she's running a lot of that research in that area. So Harriet will be coming after you for a presentation in the near future. Thanks very much for that. And there's been other questions. I'm sorry I haven't been able to go through all of them. Short time. I know Steve Barraclough wants to come back in with some admin. So if I can hand back to Steve. And before I go, thanks very much to all of you, to Jean, to Lucy, to Susie, to Fiona. Excellent presentation. Thanks very much.
Thank you.
Well done, everyone. To our panel. The internet has not been our friend this evening. To those of you who have had technical difficulties, we apologise for that. Certainly, when you can't see the slides, I think our panel have done a tremendous job. So well done. Again, apologies if you've suffered internet connectivity issues this evening. Okay, thanks very much for being with us. If you've enjoyed this, we have another presentation on the 1st of July, looking at how human factors can help us in terms of equality, diversity and inclusivity issues. So that's 1st of July at 4 p.m. I hope you might join us for that. Other than that, the chat room will remain open for perhaps 5 to 10 minutes or so for you to say final goodbyes, to perhaps ask our presenters something, if our presenters are here. So that will be the case. Other than that, we thank you very much for joining us, and we look forward to seeing you on a future presentation. To our panel again, thank you. To everyone, goodbye.